Okay, so I have the great pleasure of introducing our plenary speaker today. First plenary speaker, Federico Ardila. Federico is a professor of mathematics at the San Francisco State University, SFSU. He has been at the SFSU since 2005. He became a full professor in 2016. He got his PhD in 2003 at the MIT under the supervision of Richard Stanley. He also got his first degree at the MIT. Of his many honors, and I will just mention one. So he was an invited speaker of the ICM, of the International Congress of Mathematicians, in 2022. And let me now quote from his page. He writes, I'm a mathematician working in combinatorics and its connections to geometry, algebra, topology, and applications. He also writes, I work towards fostering an increasingly just, equitable, and welcoming community of mathematicians that benefits from our differences and serves the needs of all communities. Federico is a Colombian, and he, in fact, has strong ties with his country of origin. In fact, I said he's from SFSU, but I now see that he also is from the Universidad de los Andes in Bogotá. Now, let me again quote his own words. So in a very interesting article in the Notices of the AMS from 2016, so he wrote an article called Todos Cuentam, Cultivating Diversity in Combinatorics. So in 9 years, the combinatorics initiative between the SFSU and the nation of Colombia has built an active community of more than 200 mathematicians, most of whom are members of underrepresented groups in mathematics. More than 50 have pursued PhD in mathematics. And he goes on to give an account of his most successful project in Colombia. But now coming back to Rio de Janeiro and today's colloquium, today's plenary talk, Federico will speak about the geometry of geometries, matroid theory, old and new.
Obrigado, muito obrigado por la introducción. Muy buenos días, mi gente. Não vou torturar vocês tentando fazer minha palestra em português, mas sim quero compartilhar algumas palavras em portunhol, que é o que eu falo. Hoje de manhã, Marcela Lemos me fez duas perguntas para o IMPA. Uma, como você se sente participando do colóquio? E dois, como é sua relação com o Brasil? Isso me deixou pensativo todo dia. Estou muito, muito grato pelo convite. É um grande prazer para mim estar com vocês, tantos velhos e tantos novos amigos. Eu sei que não é um país perfeito, mas o Brasil é uma grande referência para mim, como matemático, como educador, músico e jogador de futebol. Um país que não quer sacrificar o jogo bonito, mesmo que isso signifique vencer. Me ensinou muito isso. Isso também é um bom ensino de matemática. Eu não sei explicar o que a música de Mateus Aleluia significa para mim. A música de Ilhaie, seus projetos educacionais significam tanto, tanto para mim. A música de Roberto Mendes, basada em um velho ditado sudanês que diz: vou aprender a ler para ensinar meus camaradas. Você conhece? Vou aprender a ler para ensinar a meus camaradas. Significa muito para mim essa canção, que é música e é educação. O que me influenciou a mim, Paulo Freire, e sua escola, Bárbara Carine, a conversa de Antem, a liderança das mulheres negras, das pessoas trans na comunidade brasileira, é uma grande influência para mim, uma grande ensinança. E o que significa vir a um encontro matemático latino-americano que sabe, sem sombra de dúvida, que quizás faça matemática de nível mundial. Para mim, desde Colômbia, é uma grande inspiração para mim. Então, muito obrigado pela invitação e vamos a falar de matemática. ¿Entendió más o menos? Esta palestra es basada, oh no, English, right? This will go better if I do it in English. This talk is based on my contribution to the proceedings of the ICM 2022, called The Geometry of Geometries, Matroid Theory, Old and New. If you want to see much more information, a lot of references, and a much more thorough account of what I'm going to say, that paper, you can find it, and also the slides of my presentation, a version of the slides is on my website in case you want it later. And I forgot to say this, but I will be talking about matroids. I do not assume that you have ever heard what a matroid is. But I hope to convince you that matroids are very beautiful. I hope to convince you to learn about matroids. And I forgot to write, and some of you told me that you used a YouTube channel that I have. I am apparently a YouTuber. I didn't want to be a YouTuber, but I have an online course of matroids. It's 45 hours of talking about matroids. So if you really want to learn about matroids, there's much more information. Today I will give you a glimpse of some of the classical ideas in matroid theory and try to give you an idea of some new developments and why the mathematical community is so excited about matroids these days. I'm going to talk about the work of many, many people, including many co-authors, many students, many teachers. So you can see some of their names there. And the summary of my talk, what I want to try to convince you is that matroids, which I will explain what they are, initially people thought of them as very combinatorial objects, but I want to try to convince you that they are also very geometric objects in nature. And the fact that matroids lie at the intersection of combinatorics and geometry helps combinatorics and it helps geometry. That's the summary of my talk. And there are two visionary remarks that I wanted to share with you. One is from a paper of Gelfand, Goreski, McPherson, and Serganova in 1987, where they say, we believe that combinatorial methods will play an increasing role in the future of geometry and topology. So this is combinatorics helping geometry, helping topology, 1987. And there is a quote of R.C. Bose, quoted by Kelly and Rota in 1973. We combinatorialists have much to gain from the study of algebraic geometry, if not by its direct applications to our field, at least by the analogies between the two subjects. So the idea now of geometry at the service of combinatorics. And when I look at what combinatorics looked like in 1987 and 1973, there was not so much evidence for just how strong these statements are. And when we look at the state of the intersection of combinatorics and algebraic geometry, this is really, it seems very prophetic to me. Okay, so one motivation, coloring maps, okay? I could start with many motivations, but this is one of the ways to tell you what a matroid is, why to study matroids. So here's the map of Brazil. Of course, in maps like this, usually the states are colored. Are they called states, departamentos? What are they? Estado, okay. The states are colored in different colors, and of course, you can repeat colors, and you want to repeat colors usually because if you put everybody of a different color, then it can look, it's an aesthetic choice, but generally people tend to choose fewer colors. But of course, you don't want to put two neighbors of the same color because you would not be able to tell them apart. And Guthrie in 1852 was a very young student. I think he was maybe 19 years old, and he was coloring a lot of maps. And he told his teacher, "Teacher, any map that you can give me, I can color it using only 4 colors." Okay. If you look at how many colors are in this map, I think there are 5 different colors. What Guthrie would say is that if somebody gave him the map of Brazil, he would be able to color it using only 4 colors. Okay? And so this became known as the 4-color conjecture, and it was an inspiration for many, many years of development in combinatorics. And finally, this became a theorem in 1976. And actually, it was a very controversial theorem. We don't usually call theorems controversial, but the reason it was controversial is because it was one of the first examples in mathematics where the proof involved a 1,000-page document and hours and hours and hours and hours of computer work, where they had an argument that reduced to a finite number of maps that they could not color by hand, and so they had a computer. It's like the first instance of big data in a mathematical proof. And it was a big controversy whether that was a proof or not, but today we accept that that's a proof. But what's interesting is that I would say that still today there is no kind of conceptual proof that really explains why 4 colors are sufficient. Okay? And this is one of the reasons that people wanted to develop ideas in matrix theory. So Birkhoff had this idea in 1912 to consider something called the chromatic polynomial, which is to say, not only do I want to prove that a coloring exists, I want to see if I can count them. Okay, so let's say that I have q different colors, and now I want to count the number of proper colorings. Okay? One thing that I didn't mention is that I'm looking at what's called the dual graph, where I put a vertex for each state and an edge for each border. Okay? By the way, preparing this talk, I learned that Brazil cannot be colored with 3 colors. 4 colors are necessary, and that's a nice exercise for you, and it's not so obvious actually. And I would just tell you that if you happen to be coming from Goiás, you have an advantage. So that's a thing for you to think about. Why is it impossible to color Brazil only with 3 colors? You need 4. Okay? So Q is going to be the number of colors now, and we're going to say how many colorings are there. Okay? So this is a graph. Now I'm coloring the vertices of the graph with the idea that if 2 vertices are joined by an edge, they should get different colors. So for this vertex, I can color it with any of the Q colors. Now here, I can use any of the colors except for the one that I just used. So there's Q minus 1 possibilities. Then here, I have one color that is not allowed, which is this one. So I have Q minus 1 possibilities. And then here, out of the Q colors, there's 2 that I cannot use, which are this one and this one. And I know that these 2 are different because they're neighbors. So that's why it's Q minus 2. So the number of colorings of this graph is Q times Q minus 1 times Q minus 1 times Q minus 2. And that is known as the chromatic polynomial. It's not obvious, but it is true that this is always a polynomial. For any graph, the number of colorings with Q colors is a polynomial function of Q. This example is misleading. This example might make you think that computing these is very easy. But I chose an easy example so I could do it in front of you. But computing this is actually fairly difficult. And so then the idea was, okay, well, the 4-color theorem is the same as saying if G is a planar graph, so it can be drawn on the plane, then 4 is not a root of that polynomial. If 4 is not a root of the polynomial, then the number of colorings with 4 colors is not 0, which means that a coloring exists. It's a strange idea, but it led to the idea that maybe we should look at this polynomial and try to think of it analytically as a polynomial, not just as a combinatorial thing. Okay. There are many beautiful papers about the locations of the roots of chromatic polynomials. And the idea was, how do we prove that 4 is not a root? It's a fascinating story that I don't have story to say today, but it has not been successful. Okay? But as often happens in mathematics, you try to do one thing, you fail, but then you do some other beautiful thing. And this is what I want to tell you about today, is that even though this has not succeeded in giving a conceptual proof of the 4-color theorem, it has given rise to some beautiful mathematics. So I want to show you a big chromatic polynomial. I wanted to show you the one of Brazil, but I think maybe this is an open problem. Es una pregunta abierta para los alumnos. Calcule o polinômio cromático do Brasil. Se você lo hace, não é tão fácil, mas você vai aprender bastante a hacerlo. Pienso que puede ser una semana o una tarde, no sé, mas creo que es posible. Una pregunta para los alumnos. ¿Qué você percibe sobre el polinomio cromático dos Estados Unidos? He conocido este artículo this article computes this polynomial, okay? And if you want to compute the polynomial of Brazil, I suggest that you look at that article because this article made me realize that I did not know how to compute big chromatic polynomials, and they do it, and this is it. And so I would like to ask tres alumnos que me digan, ¿qué você percibe sobre el polinomio cromático de los Estados Unidos? Por favor, no sean tímidos. ¿Qué observan? Los números suben y bajan. Increase, and then they decrease. Los coeficientes. Is there anything else that anybody notices? The sign goes plus, minus, plus, minus, plus, minus, plus, minus. Theorem, any chromatic polynomial goes plus, minus, plus, minus, plus, minus. This is a theorem that takes maybe one afternoon to prove. This is not obvious. One afternoon to 1 week. It's not obvious. The proof is not very difficult, but thinking of the proof is not so easy. The observation that the numbers go up and go down is very hard to prove. Any other observations? This was just my bad picture. It's interesting. So I asked my students, I live in San Francisco, and I don't know if it's because I live in San Francisco or because of the colors that I chose here, but what my students said is it looks like a rainbow. It's an arcoiris. See? When they said this, I finally understood what log concavity means. So log concavity is this inequality. Okay, it's some inequality. Now, arcoiris don't go like this. Arcoiris are concave. Okay, so this is a concave function, and if you look at how, this is something else that I'm going to say something that's very easy, but that I only understood 2 years ago. How long is a number? It's the logarithm. That is what a logarithm means. I only understood as a 44-year-old that a logarithm is the number of digits. And so if the logarithms form a concave function, that means that the numbers form a log concave function. So when we say log concave, and you'll find that many mathematicians are very interested in log concavity, and that just means it has the shape of a rainbow. Okay. This was observed by Giancarlo Rota, my professor at MIT in 1970. And when I learned matroids from him, he told us, I'm going to die and I'm not going to see the solution to this problem because mathematics is not ready. We need a new idea, and I just won't live to see it. Jun He, in his PhD thesis in 2011, proves this result. And this was when people first started saying this could be somebody who might win a Fields Medal one day. The reason that he won a Fields Medal is because he developed the kinds of techniques that are able to tackle combinatorial problems like this. And so I want to tell you a little bit about how one proves these results like this. And maybe one thing that I would say is that if you are log concave, you are unimodal, meaning that you go up and then down. So that this observation is also good. So log concavity theorems from Jun He, that the coefficients of the chromatic polynomial are log concave. And if there is time, and I'm not sure if there will be, I also want to tell you about another result that we proved with Jun and with Grant Denham. That's something called the Schelling polynomial of a graph and of a matroid. Those coefficients are also log concave. The simplest way to state this is like this. This doesn't explain why this is an important quantity, but there are reasons why that's an important polynomial. It's a fact that if you can show this log concavity, you can show this something being very strongly log concave, and so the second one is a much harder result, and so we had to develop a lot more geometry than was initially developed. And so I hope to be able to tell you a little bit about this story. Okay? So why do we care about unimodality log concavity? Why, I mean, rainbows are beautiful, and maybe that's enough reason. Sometimes you see something beautiful, you want to understand it. One thing that happens is that many combinatorial sequences are often positive, unimodal, log concave. An example is binomial coefficients. If you take a row of Pascal's triangle, it's positive, unimodal, log concave. And if I ask you to prove that, and I give you the afternoon, you will find a proof. So sometimes the proofs are quite easy. But if you don't do it in an afternoon, you probably won't see it in 20 years. This seems to be what happens in these kinds of problems, is that either they're pretty easy, or they end up being kind of long-standing open problems, and they usually require a fundamentally new construction, a fundamentally new connection. So usually what you have to do is just develop something completely different, understand something completely new about the sequences, and then as a consequence, you're able to get unimodality log concavity. And this often involves connecting to other fields of mathematics where there are tools to prove positivity, unimodality, log concavity. So it might seem strange, but I am the kind of combinatorialist that when I see a number and it's positive, what I want to find is a homology group that has that rank. This is one way of proving that something is positive. And there are many quantities in combinatorics where the only proof that we have that a number is positive is that we are able to come up with some topological construction that verifies that this is just the rank of some vector space, so it's positive. To show that something is unimodal, the most common techniques are using representations of the Lie algebra SL2, which if you have studied them, they are unimodal. The Haar-Lefschetz theorem from algebraic geometry, which we heard about in yesterday's session in this room, are ways of proving unimodality. And for log concavity, you have to work significantly harder, developing things like Brun-Minkowski theory, which is coming from measure theory, the Kowalski-Tessier inequalities, and Hodge theory coming from geometry. Okay. And so in the end, what we usually learn is how these objects that maybe seemed kind of innocent and combinatorial are very deep. Their combinatorial objects are extremely deep, and by understanding their depth, you are able to understand why they have these simple numerical properties. Okay, so with that kind of general introduction, let me tell you a little bit about what matroids are. So matroids, the idea of matroids is that they capture the combinatorial essence of what does it mean to be independent. There are many notions of independence in mathematics, and matroids realize that there is a lot of similarities between them. The simplest and the first example was if you start with a set of vectors in a vector space. So here is R3, and I have 5 vectors. The vector A points vertically, and the vectors B, C, D, and E are on the floor. Okay? And you want to ask, what are the bases that I can make using that particular set of vectors? Okay? So if you want to make a basis using only these 5 vectors, well, this is R3, so I need 3 vectors. I know that if I want to span anything vertical, then I have to include A. Otherwise, I would stay on the floor. So A is mandatory. And then in the floor, I should choose 2 vectors. And those 2 vectors can be any 2 except don't choose D and E. So you must choose A, and you cannot choose D and E together. That's the condition. And then these are the 5 possibilities that arise. Okay? And this is what's called the matroid. That's the matroid. What are the bases that you can make? Each one of these is a set, but I don't want to put so many brackets, so it's a set of sets, a set of bases. Okay? Now, maybe you learned in a linear algebra course that bases have something called the exchange property. That if I have 2 bases, one in each hand for the same vector space, if I take out a vector of my first basis, I can replace it with a vector of the second basis. and I'll get a basis. It's a simple exercise to prove this. Again, it's interesting how the history of mathematics works out that in 1935, in the US and in Japan, in exactly the same year, two people came up with exactly the same definition. Nakazawa and Whitney defined a matroid to be anything that satisfies this property. Okay? So if you have some set and some collection of subsets that satisfy this exchange property, that's what's going to be called a matroid. So I'm trying to explain to you that the definition of a matroid is very simple in the sense that it's short. Of course, there's a lot of depth that you find later, but I just want to show you it's a short definition that is supposed to say what is independence about. Now, what Nakazawa and Whitney realized very early is that graph theory also has this property. If I take a graph and I look at the spanning trees of the graph, so a spanning tree is a set of edges that connects the whole graph and has no cycles. It's a tree. Yeah? So if you want a spanning tree, you have 4 vertices and you need to connect them. So to connect 4 vertices, you need 3 edges. And again, you see, well, if I'm going to connect them, then I have to use A, and I cannot use both D and E. So the constraints are the same, the answers are the same. So the spanning trees of this graph are giving me exactly the same matrix. Okay? And they realized that for any graph, the set of bases also satisfies this exchange property. And they said, okay, so it seems like linear algebra and graph theory have something very fundamental in common, and that's why they decided, let's invent matroids to be whatever looks like linear algebra and like graph theory. Okay? But these were the 2 examples that they had in mind. But a lot of people came into the party uninvited. So, for example, later they realized, oh, when we teach a course in Galois theory and you talk about a field extension, you talk about algebraic independence. Algebraic independence also satisfies this property. Okay? And if you've taken a course in field theory, you have proved that in some way or another. If you have a problem in matching theory where you have a set of jobs and a set of people and you're trying to match them, that problem also has the structure of a matroid. If you have a problem in routing where you're trying to direct traffic in a network from here to here, so you have a bunch of routes that should not intersect with each other, that also has the structure of a matroid. And there's many, 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 many other examples. And so one nice thing about matroids is that they have a simple definition, but they have, like a good theory should, many, many examples to apply to. Okay? And one point that I want to make is that the unintended examples are equally fundamental to the theory, even though people didn't necessarily think of them at first. So here's a very, very old question from the origins of matrix theory. Are matrix geometry in the sense that they come from pictures? And so let's say that a matroid is linear if it comes from linear algebra, if it comes from a set of vectors. Okay? So I told you that a set of vectors leads to a matroid, but now we ask the reverse question. If you have a matroid, does it come from a set of vectors? Are they all linear? Well, you can imagine, because there is something called linear matroids, that the answer is no. Linear matrix versus all matroids. So Whitney very early realized that some matrices are nonlinear, although it's kind of hard to think of one, but then it's possible to do that. And he was disappointed, and many people were disappointed because they were trying to axiomatize linear algebra. And they were thinking, we're missing an axiom then. What is the additional axiom that we can make so that this is really linear algebra, so that every matroid comes from linear algebra? And so there was a quest for what they used to call the missing axiom of matroids. There is a beautiful paper from Mayhew and others. The title of the paper is called Yes. And then the subtitle of the paper is, The Missing Axiom of Matroid Theory is Lost Forever. It's a very dramatic title. That paper is a paper in logic, actually. And it's a paper that explains that you cannot axiomatize linear algebra. And I'm not an expert in logic, but I could point you to what exactly that means. But it's a paper saying there's not a way that you can axiomatize. So you have to deal with these people that got to the party and you didn't invite them. Okay? And then I think it's very surprising and even a little embarrassing that only 5 years ago were we able to understand that basically all matroids are nonlinear, essentially. So I don't mean all, but I mean asymptotically. So if you fix an n and you ask out of the matrix of n elements how many are linear, you find that none of them are linear. Okay? And it's interesting because almost any matrix that we think of is linear, and I think that just talks about our kind of lack of imagination a little bit. It's like if I ask a random crowd, say a number, they're probably going to say an integer. But we all understand that almost no number is an integer. Almost no number is rational, but almost any number that we think of is rational. It's a similar thing. Almost nothing is linear, but almost anything that seems natural to us is linear. But there's linear matrices are tiny, matrices are much bigger. And again, this is not a flaw of the theory, and one of the most important points that I'm trying to make is that nonlinear matrices are really fundamental for this to be a robust geometric theory, which is a little bit ironic because people didn't want them because they wanted to have pictures. And I'm trying to say that if you want pictures to have a robust theory, you want all matrices. Okay? And maybe I will tell you that there was also a battle in matrix theory where Rota, who was a very interesting mathematician, had very strong opinions, and I found myself agreeing with many of them. He thought you cannot have a theory with an ugly name. Nobody's going to want to study matroids. He would talk right about the cacophonous word matroids. And he would say we should call them geometries. People will want to study geometries. People are not going to study matroids. And he actually wrote a book and he called it Combinatorial Geometries. But he lost the battle, and so we called them matroids. Okay? But one reason that I tell you the story and why I call my talk The Geometry of Geometries is because, again, I think that it was very visionary of Rota. I think he understood how geometric the theory was in a way that I don't think other people understood, or maybe I don't think he fully understood actually, but I think he would be very pleased today to see how geometric the theory has become and how really geometries were a good name. And actually, in Jun Ha's most famous paper, he calls it Hodge theory for combinatorial geometries. I think he agrees. So today I'm going to share with you, I say at most 4 because I doubt I will get to show you everything. I prepared some slides, but I think it's more important to be clear than to be fast. So I will share at most 4 geometric ways of thinking about matrix. And for each one, I'm going to tell you what's the definition, what's the kind of geometric picture, why is that a picture that's interesting, the geometric motivation for it, and how that helps. How it helps us understand matrix and how it helps us understand things outside of matrix. Okay? So the first example I find very beautiful, and it's something called the matroid polytope. Okay? So for the matroid polytope, what you're going to do is you're going to take your matroid, which is a list of bases, and then each one of these bases is going to turn into a point in space. If your set has 5 elements, then this is going to be a point in R5. And so for example, ABC, the indicator vector of ABC is 1, 1, 1, 0, 0. ABC are in, D and E are not in. Okay? So for each one of these things, you encode it in a 0, 1 word of who is in the basis, who is not in the basis, and you get a cloud of points, and you take the convex hull, you kind of wrap it in plastic, and the shape that you get is called the matroid polytope. Okay? This is a definition of Edmonds in 1970 and of Gelfand, Goretzky, McPherson, and Serganova in 87. And I think in mathematics, sometimes we are too obsessed with who got there first. Edmonds got there first, and he should get credit. And Gelfand, Goretzky, McPherson, and Serganova got there also in a very different way, and I think it's important to remember both ways. So what was Edmonds trying to do? Edmonds is coming from combinatorial optimization. And he was really interested in spanning trees and in computing like the minimum spanning tree problem. And in combinatorial optimization, it's a very common technique. When you have a combinatorial problem, make a polytope out of it. And so that's what he was thinking, and that's how he found this polytope. And then combinatorial optimization problems become optimizing a linear function over this polytope. It's a very beautiful story. Gelfand, Goretsky, McPherson, and Serganova had a very different way of getting there, which is that they were studying the geometry of the Grassmannian. And I will talk about the Grassmannian for just a minute. Forgive me if what I say doesn't make sense. So the Grassmannian of K-planes and n-space is some kind of variety that has a torus action acting on it, a torus acting on it. If you take a point in the Grassmannian, the torus moves it around. You take the closure of that, and that's what's called a toric variety. And toric varieties that are embedded, like this one is, are in a dictionary with matroids. So, with polytopes, I'm sorry. And so they say, well, if I'm in the Grassmannian, which is a very natural geometric object, and I take this variety, toric variety, which is very natural, it should correspond to a polytope that should be beautiful. And the polytope they found turned out to be exactly the same one that Edmonds had discovered. And I think that's a very beautiful story because actually, the way the theorems in this field are proved, you end up reading the optimization literature and the algebraic geometry literature. And they proved this very beautiful theorem, which is formally stated by Gelfand, Goretsky, McPherson, Serganova, and Edmonds perhaps didn't state it exactly like this, but he would have known how to prove it, which is this. The first part of the theorem is that when you take this matroid polytope, any polytope has edges. And it turns out that the edges of this polytope are all of the form EI minus EJ. EI minus EJ, where the EIs are the unit vectors. So for example, if I look at this vector from here to here, if I subtract these two, I get 0, 0, 0, 1 minus 1, E4 minus E5. And so they showed for any matroid polytope, any edge is of the form EI minus EJ. And I already think that's beautiful enough. But I think what's incredibly beautiful is that the converse is also true. That if you're able to make any polytope whose edges are of the form EI minus EJ, then it's a matroid. Okay? And maybe some of you have played with this thing called zone tools, where they give you it's a thing of like sticks, and you make polytopes out of it. But the sticks come in very specific directions and angles. And so here, what this picture is supposed to represent is that here is what's called the root system of EI minus EJ, all the vectors in EI minus EJ. And the question is, what polytopes can you make using only those directions? It's a very natural question. You have a bunch of directions. How can you turn that into a polytope? And it turns out that if you can do that, then you have a matroid in your hand, and that's an if and only if. I think this is a very beautiful theorem. And so I could define a matroid to be a polytope with edges EI minus EJ. And I think this is one of my favorite definitions of a matroid, which turns out to be equivalent to the one that I showed earlier. Okay. So I find this very nice. And one thing that I like about this is that if you want this theorem to be true, then you have to allow nonlinear matroids in the story. So if you want to be able to describe matrices geometrically as these beautiful polytopes, then you need to allow linear matroids, graphical matroids, algebraic matroids, matching matroids. All matroids need to be allowed into the theory for this to work. Okay? So matroids somehow provide the correct level of generality for this theorem to be true. Okay? So what I'm going to do now, I don't love it when people do this. I'm going to put a very busy slide. I'm just going to put it there, and I'm not going to talk about it. Okay? All I'm going to say is that if you see something there that is interesting to you, then I am happy to talk to you about it later. I can't help to say a couple of things. One, matrices have the structure of a Hopf algebra, if you know what that is. This is something that Rhoda discovered. But it turns out, and this is something that we discovered with Marcelo Aguiar and with Mario Sanchez, if you want to understand this Hopf algebra, you have to think of the polytope. Okay. The other quick comment that I want to make, because I know that there are people in this room who love Lie algebras, is that you cannot see this collection EI minus EJ and not ask a lot of questions. This is, in my view, the most important configuration of vectors in mathematics. It is what's called the type A root system, which has this Dynkin diagram that looks like this. And so you have to ask, well, what about the other Dynkin diagrams? And then you have a beautiful theory. Okay? There's a lot to say here, and again, if you have questions, let me know. So I will pause for a moment, look at the time. And tell you about the second geometric model, which is called the Matroid fan or the Bergman fan. This is something that, that we did with Carly Clivans, who I think some of you know because she spends a lot of time in Rio. So now let me take a matroid, and instead of thinking about the bases, I want to think of the flats. Okay? And the flats are going to be the spanned, this should say spanned subspaces or span sets. Okay? So what I want to say is, okay, in this picture, what are the lines that I can make? I can make the line A, I can make the line B, I can make the line C, but if I want a line through D, it's also going to include E. So that's why I put here, A, B, C, and D, E. Then I look at what are the planes that I can make. So A and B form a plane, A and C form a plane, A, D, and E form a plane, and then the floor forms a plane. So those are the things that I put here. And then I have the whole space and the origin. So the flats are basically the subspaces. Okay? This is very classical. Now, what we did with Carly Clivans, inspired by some work of Bernd Sturmfels, is to make this into a matroid fan. So a fan is the word abanico. ¿No? ¿Cómo se dice abanico? ¿Alguien ayuda? Lecky. Okay. Fan in this sense, it's a bunch of flat things that are connected to each other. That's what fan means. So first I have to tell you what is the skeleton of the fan. So the skeleton are these rays, and I have one for each one of these things. So I have A, B, C, D, E. That means I have A, B, C, D, E. I have one for each one of these, okay? But this is not put in a random place. This is put in a very specific place. When I put an A here, this means the vector 1, 0, 0, 0, 0. When I put A, D, E here, this direction is very specifically the direction 1, 0, 0, 1, 1. Okay, there's very specific directions. So you get these kind of rays going to infinity. And then I have to say, how do I build the fan? What are the leaves of the fan? Okay? And what I do is that I say, okay, well, I'm just going to put, for example, a leaf between B and BCDE because B is contained in BCDE. But for example, AC and DE are not comparable. Neither is contained in the other. So if I look for DE and AC in this picture, they are not connected by a fan. So this is the matroid fan. And if you didn't follow the details, the point is it's a very specifically constructed matroid fan using the combinatorics of the matroid. So definition theorem. Why do I say this is a definition theorem? This comes from the field of tropical geometry. I don't love the name tropical geometry. And I want to ask if you are a Brazilian who has opinions about the name tropical geometry, tell me. But you should know, in case you don't know, that tropical geometry is a field named by French people in honor of a great mathematician, Imre Simon, Hungarian mathematician who worked in Sao Paulo. And so for that reason, this is called tropical geometry because it has roots in Sao Paulo. And when I went to the first conference in tropical geometry and I was the only mathematician coming from a tropical country, it seemed a little strange to me. And I seriously, I'm very curious about this name. What you think of it? If you know more about it, please tell me. But I want to say that that's the name, and I don't like it, but that's the name. Tropical geometry. So what is tropical geometry? It's a beautiful field. I mean, I like the field. So what it says is you take a let's, in the simplest case, let's say that you take a projective variety, a projective algebraic variety, so it's curvy. This might be like a paraboloid or something. And what you're going to do is that you're going to look at the behavior at infinity. Okay, and I'm working over the complex numbers. So what I do is that I just look at what are the directions that it goes to infinity, and this is what this logarithm does, is that I'm taking a limit which is just looking at the directions at infinity. Take the variety. If some of you played with logarithmic paper, which if you were to plot a variety in logarithmic paper, it ends up having these very clear directions to infinity, and those directions are the tropical variety. And you end up with these pictures that look like this, that are piecewise linear, and that are basically telling you, I don't know exactly what happens in the middle of the variety, but I know its behavior at infinity, and it's piecewise linear. Okay? Now, it's very surprising that actually it's a very powerful technique. There's a lot of very difficult problems in algebraic geometry where you can say, you know what, let me tropicalize the problem, and now it becomes a very hard combinatorics problem. And geometry is hard, combinatorics is hard. We're both hard, okay? But it's a change in language that because you have things that are piecewise linear, if you are like me and you like polytopes and you like fans and you like combinatorics, then you have a technique for proving geometric theorems. I was sitting in a beautiful talk yesterday about severity degrees, and this is the kind of thing you can actually compute severity degrees tropically by saying, let's just see the behavior at infinity, and there's things that you can do. Now, one of the first questions was, okay, that sounds like a nice theory, but what do tropical varieties look like? And one of the first questions, which was a very basic question, is what if I just take a plane and I tropicalize it? So it's like the simplest variety is a plane. I almost struggle to understand that a plane is a variety because it's given by linear equations, which are polynomial equations. So what happens when you take this very simple variety and you tropicalize it? Our theorem is that you get that fan. And so that fan was not constructed arbitrarily. Our theorem is that if you start with any linear space in the complex space and you tropicalize it, the answer is a matroid fan. And so that's why matroid fans are important, because they are the tropical analog of something linear. It's a very fundamental thing. Okay? And this, we can prove that it's a wedge of spheres and so on. Now, I want to tell you about a theorem. So one very nice thing about tropical fans, like this, is that they have something called zero tension, meaning that this is like in physics, where at any juncture, you're being pulled with equal forces. So for example, if you stand here, you see that this pulls you with equal force as this. Or if you stand with ray A, you find that there's three things that actually form equal angles and are pulling at you at equal strength. So tropical fans always have this property that in each ridge they're being pulled at in a balanced way. This is called the balancing condition. And so you can define a tropical fan independently of algebraic geometry to be a tropical fan is a fan that balances. Okay? And then you can say, okay, tropical fans have something called a tropical degree. Just like varieties have a degree, tropical varieties have a tropical degree. And one early theorem in tropical geometry is that if you want the degree of a classical variety, you can tropicalize it. And the tropical degree here is equal to the classical degree here. So tropical geometry gives you a way of doing this. But there's this very beautiful theorem proved by my student Alex Fink in his PhD thesis in Berkeley. A tropical fan has degree 1 if and only if it is a matroid fan. Okay, so I told you that if I start with a linear space and I tropicalize it, I get a matroid fan. And because linear spaces have degree 1, that means that the tropicalization also has to have degree 1. But there's many matroids that don't come from all the matroids that are not linear don't come from classical algebra, so you cannot pull back and say this has degree 1 because that had degree 1. You have to ask intrinsically, what are the tropical things that have degree 1? And you find that the class that satisfies that is, again, exactly the class of matroids, and not just the linear matroids, but all matroids. And so if that got a little bit too technical, what I want, the summary is, you can say a matroid is a tropical fan of degree 1. And degree 1 means linear. So really you can think of a matroid as just what it means in tropical geometry to be linear. It's a very fundamental thing, and that's why all of a sudden, if you want to do tropical geometry, you have to learn some matroid theory. And again, from this point of view, from this geometric viewpoint, all matroids are equally natural. Okay, so you have to include nonlinear matrix. So what are some applications of this? The one that is most celebrated is the work of Junha and many of his collaborators in what became known as the Hodge theory of matroids. So he wanted to prove low-concavity results using tools from Hodge theory, because in Hodge theory there are techniques to prove that things are low-concave. But what he found is that Hodge theory was not strong enough, because most matroids don't come from geometry. Most matroids don't have Hodge theory applying to them. And so what he said is, maybe we can develop a combinatorial version of Hodge theory that applies to matroids. And in this very celebrated paper with Adiplacito, Ho, and Katz, that's what they do. They prove a version of Hodge theory specifically for those fans. So what they show is that this matroid fan that I showed you that we constructed with Carly Clivens, for some very strange reason, and I don't think that anybody fully understands it, this looks like the Hodge theory applies for these things. Okay, and so if you're familiar with words like Poincare duality, Hart-Lefschetz, Hodge-Riemann relations, all of that is satisfied by this ring that is completely combinatorial, and I think it's fair to say that it's still a mystery why that is. So they had to work really hard to do that. But that is at the root, and so the playground of that proof is this matroid fan, and that's how you prove that these coefficients are low-concave. So if you want to understand why, when you compute the chromatic polynomial of Brazil, it will look like that. It is because of this Hodge theory. That's what's at the bottom of it. Okay, and if you are interested in talking about that, let me know later. Let me talk very, very briefly about a third model, which is called the conormal fan. Okay, and this one comes from a very fundamental idea in matroid theory, which is that every matroid has a dual matroid. And it's very simple. You take the basis of your original matroid, and now you take the complement, and that gives you the dual matroid. It turns out that matroid duality generalizes simultaneously like the orthogonal complement in linear algebra and graph duality, which I actually find very beautiful, that orthogonal complements and graph duals are the same concept. Okay? And so we define with Junha and with Grant Denham, we define the conormal fan to be basically the Bergman fan of the matroid times the Bergman fan of the dual. So we're interested in how the matroid fan of the matroid and its dual interact. And this is basically the tropical version of the conormal bundle. That's what we're doing here. So this is all geometrically motivated. And then we have to work very hard. So we find that this variety, this tropical variety that we construct, if our matroid is linear, it is the tropicalization of a very beautiful variety constructed by Varchenko. This has to do with incidence varieties, with conormal varieties, maximum likelihood degrees. And so these are kind of the roots of what we're doing. And we are also able to show, and this was an extremely hard work to show, that these fans also behave as if they were smooth projective varieties, and they somehow don't have the right to behave in this way. But when you look at the Chow ring, which is what controls the intersection theory of these things, the Chow ring of this conormal fan looks like the Chow ring of a projective variety, a smooth projective variety, and that's what we use to show that these coefficients are low-concave. And again, if you're interested in these kinds of things, there's some beautiful algebra, beautiful geometry behind the scene, some beautiful combinatorics. And I think I told you that I would talk about at most 4 models, and I think it's going to be 3 models that I talk about. So with that, I would like to thank you for your attention.
Thank you very much for this beautiful talk. Amazing and so wide. And so I would like to invite you for questions or comments.
It's okay. So the question is why are they called Metroids? It's a beautiful question that I have been thinking a lot about this week, and let me explain why. So the reason originally Metroid is because it generalizes matrix, which I don't think that's a great reason, but that's I mean, I somehow agree that it's not a great name, but except I just spent last week in Bahia. And I don't know if this is a Brazilian thing or a Baiano thing, but everywhere you go in Bahia, a gente fala de la matriz, las religiones de la matriz africana. And I'm a musician, and I was doing some percussions of Afro-Colombian music and a conversation between Afro-Colombian and Afro-Brazilian musics, and people kept asking me, ¿cuál es la matriz africana de la música colombiana? And I have a new relationship with the word matrix, because now I think a matrix is not just this, and I should know this because in Spanish, matriz means matriz as in Portuguese, and I think in English the word matrix doesn't mean the womb, it doesn't mean the mother, it doesn't mean the origin, and I actually might be in the process of reconciling myself. I think maybe instead of calling it Metroid, I think we should call it matriz. Because I really have been thinking about this because it's somehow saying, okay, you have some object, and it has something associated to it that really tells you a lot about the essence of that object, and this is like la matriz. I actually find it, and you can have different settings, like the Lie group of type A and the Lie algebra of type A. You can tell that they have the same matriz, which is the Dynkin diagram like this. And so I've been thinking that this is my partial answer, but like, I should say, I share this in the spirit of, this quote that I was sharing at the beginning, and I'll say it in English, in this beautiful song, Macemba, by Roberto Méndez. He talks about, voy a aprender a leer, para enseñar a mis camaradas. And it means I'm going to learn to read so I can help my comrades. And there's a very deep political and racial and social meaning to this. But I think, for me, this is something that I think a lot about in the US. There's a very similar story called a very similar saying from the time of slavery, which is each one teach one. When a population is enslaved, anything that you learn, you teach. And so I say this to say that I have this idea that is a very partial idea, and it's an idea in progress. And I'm trying to understand the answer to your question. Like, what is, I'm spending 20 years trying to understand what a matroid is. And this is the best answer that I have so far. And I say it with humility that I still have everything to learn, but this is the best answer that I have.
More questions or comments?
So in these geometric characterizations of matroid, is it easy to characterize the linear ones?
No, it's impossible. And I think the theorem, I think this paper that says yes, the title of the paper says yes, tells you you're not going to find a nice characterization of the linear matrix no matter how hard you try.
Interesting. Thank you.
I'm not an expert in logic, but that's my interpretation of that theorem. It's a great question.
Do you know if there's some relation of matroids to logic? Because I'm thinking about we can maybe translate the combinatorics of transfinite numbers into some kind of geometry. Mm-hmm. Do you know if there exists that relation? So
there is, and actually in model theory, they don't use the word matroid, they use the word geometry. So in model theory, there's a sub-branch of model theory where they call them pre-geometries, which was the name of Rhoda. And I'm not an expert in this, but I know that the school of Hrushevsky has been doing some very beautiful work, proving some very deep theorems in model theory using matrix. So Hrushevsky would be a good person to look for. Hrushevsky, I think.
Thanks. You mentioned Brun-Minkowski. where do the Brun-Minkowski inequality enter this picture?
So the Brun-Minkowski inequality is an inequality about volumes, about something called mixed volumes. So you have the idea that a solid has intrinsic volumes. It has like the full volume, it has the surface area, and it gives you some inequalities between them. And the Brun-Minkowski inequality says something like if I take two polytopes and I multiply their volumes, it's greater than or equal to the mixed volume of them squared. And so the very, I think it's a very beautiful and very intricate idea is, and actually my advisor Richard Stanley I think was the first person to do something like this. Okay, I have some combinatorial numbers. I want to prove they're log concave, so let me invent a polytope where the volume of this polytope is my combinatorial number. And then the Brun-Minkowski inequality for the polytopes proves the inequality for those combinatorial numbers. And that's why I was saying, in the end, what's less interesting is the inequality. What's more interesting is you found this beautiful polytope, like the order polytope of a poset, the volume is equal to the number of linear extensions of the poset. This is the kind of thing that it does.
We was we here we were seeing the definition of a group a matroid earlier, yes, and as I first heard it, it sounds like somehow so topological, and so not exactly a topology, but I seen it like so mountains and so stuff. So with and it's there a relationship between topologies and matroids in definition? Like matroids is a weaker definition.
Yeah,
of
it's
topology.
It's a really great question, and I agree with you. So when you work in matroid theory, there are parts of matroid theory that feel very similar to when you're working in point set topology. And for example, in point set topology, you have the idea of a closed set. You have la clausura. I don't know how you say it. Closure, clausura. Fissura? Fissure, okay. Fissure, in matroids, matroids have a fissure. And it satisfies the same properties of the fissure from topology, but it has additional ones. So I agree with you that there's a lot of similarities. Another thing is that in point set topology, you have all these different axiomatics. You have opens, you have closed, you have fissure, and similarly in matroids, you have flats, you have bases, you have independence, which is a little bit frustrating at first, but in the end, when you learn many languages, you can say many things and you find connections. I think the main difference that I would say is that I don't know that point set topologies have a connection to algebraic geometry in the way that matroids are finding a connection. So I would say that's the main difference, as I know. But
Yes.
but there's a lot of similarity. It's a
Yes,
really
thank
good
you.
point.
This image when in the books of topology, introducing topology, this is a finite sets, and this topology is very similar to the first image I had.
I agree.
Any more questions or comments? Well, if not, let's thank Federico again.